Now we're going to talk about continuous convolution, continuous distribution convolution. For a continuous case, if we have x, this is a PDF. Now suppose x has a CDF function, that is f(x), and also PDF function f(x). Now you have y, CDF is gy, and PDF gy. Okay. Obviously, we need x, y to be independent. Now, what is f(x) plus y? And what is f(x) plus y? And let's first derive the f CDF function f(x), y. Suppose this is a. So this will be probability x plus y less than or equals to a. So this is definition. Now, here we are going to do because x plus y needs to be less than a. So we just need to do the integration x plus y less than or equals to a. Then you have f(x) gy dx and dy. So this will become minus infinity to infinity and minus infinity to a minus y f(x) gy dx dy. Okay. So this would become minus infinity to infinity, minus infinity a minus y. So let's take x out, f(x) dx, then times gy dy. So this will become minus infinity to infinity. So you see this one goes from minus infinity to a minus y. Okay. So this will be the f function, actually, the CDF function, because you do the integration all the way from minus infinity to a particular value. This is a CDF function, right? So this will become CDF f(x) a minus y times gy dy. Now we got this f CDF function. Now what we need to do is we need to x plus y. We need to do the differentiation. Then we will be able to get this PDF function. So what will be the PDF function? Which is actually equals to d over dA minus infinity to infinity f(x) a minus y gy dy. So this will become minus infinity to infinity d over dA f(x) a minus y. Because only this guy has a, right? The other guy don't have a, so this is gy dy. So this will become minus infinity to infinity, actually f a minus y times gy dy. So if you compare this function, let's compare this function. Let's look at this function. You see the inside. What's the difference from the previous one? So this is an integration. If we look at the previous one, you see here, in discrete case we have summation. And in continuous case, we have integration. And we have aj bn minus j, right? So this one, you also have y and a minus y. You still multiply them together. This is here. This is a summation. Because the range is from 0 to n, so you go from 0 to n, and aj bn minus b. aj bn minus j is actually probability mass function. The value you have actually is the f, but it's similar. So this is a continuous case. This is a convolution. What do we call convolution? In the continuous case. If you know PDF function, and you want to get the PDF function for the continuous case for the summation of two random variables, you do convolution. To illustrate the idea we just, or concept we just discussed, now let's have an example. Let's have the two independent exponential random variables. So exponential, we use the exponential to model the lifetime. It's time, right? So it should be continuous. Okay? So exponential random variable is continuous. And they are also, we have two of them. They are independent. Okay? Now, suppose x and y, both of them are exponential, and they are lambda. Now, the idea is, what is f x plus y? And you have a. Okay? So this goes from 0 to a, f a minus y times gy dy. Let's do the convolution. And this will become 0 to a lambda exponential minus lambda a minus y times lambda exponential minus lambda y dy. This becomes lambda square 0 to a exponential. You see here, this is a negative and negative, so become positive. And you have a negative lambda y here, so they cancelled. What is left is only lambda a. So minus lambda a dy. But your integration is over y, so this one will become lambda square a exponential minus lambda a. And a greater than or equals to 0. Why a greater than or equals to 0? Because exponential is always models the time. The time is always positive, right? You cannot have negative time. If you count the time, either 0 or you have some time. It's like failure time of a part has to fail at a certain time, right? What is this distribution? If the two random variables, they are exponential, you add them together, what will be the new distribution? Gamma. This is gamma. However, previously we have two Poisson, then you add them together, it's still Poisson, right? So here, this is gamma. Gamma is actually 2 and lambda. 2 random variables and lambda. So in general, if you have, what if you have gamma? If you have gamma n lambda. Gamma n lambda is actually you add n, okay, exponential random variable together. Okay. So if you have xi, maybe I change the color so that differentiate a little bit. So if you have xi and I from 1, 2 to n, so you have n random variable. And this xi, each one of them is actually exponential lambda. Now if you add all of them together, x1 plus x2 plus xn, okay? And what will be the new distribution? So the new distribution is actually gamma n lambda. What will be the function form? It will be f x1 plus x2. You add them together to xn, and then t is actually equals to lambda exponential minus lambda t, and then lambda t n minus 1 divided by n minus 1 factorial. So over here, this will become the gamma n lambda distribution. Now, if you put 2 here, if you put 2 here, now let's put this one lambda. So what we want is 2 lambda, right? So we put this lambda e minus lambda t, and lambda t and the 2 minus 1 divided by 2 minus 1 factorial. So this will become lambda exponential minus lambda t, and times lambda t, and it's actually the same as this one. Just that we are here, we are not using t, we are using a here. Here we are using t. It's the same? Is it the same? This is lambda square t, and then exponential minus lambda t. So here is lambda square a exponential, right, minus lambda a. So this is a gamma 2 lambda, and this is a gamma n lambda. So this gives a summation of 2 independent exponential random variables. Okay, so this is the end of the transformation of distributions.